This lecture will discuss descriptive measures for population. We need to distinguish between a parameter and a statistic. Basically, a parameter is a measure calculated for a population, and a statistic is a measure calculated for a sample. We may calculate mean for a population and can also calculate mean for a sample. The former is called a population mean, and the latter is called a sample mean. Similarly, we have population variance and sample variance. We also have population standard deviation and sample standard deviation. The table lists the common symbols for parameters and statistics. We use Greek letters to denote parameters and use Latin letters to denote statistics. The population mean is mu, and the sample mean is x bar. The population variance is sigma square, and the sample variance is s square. The population standard deviation is sigma, and the sample standard deviation is s. In applications, a parameter is something we want to know, but is not available due to the lack of information for the whole population. Because we can collect information from a sample, we can calculate a statistic from a sample. Therefore, we usually use a statistic to approximate the corresponding parameter. This procedure is called point estimation in statistics. Let's look at one example. The US Census Bureau reports mean annual income of US households in the publication Current Population Survey. The reported number is essentially calculated based on a sample of 57,000 households. In this example, the population includes all US households, and the sample contains 57,000 households selected by the Census Bureau. The population data contain incomes of all US households, but the sample data only contains the income of 57,000 households selected. The population measure is the population mean of income of all US households. However, because we do not have the population data, we cannot calculate this parameter. So the population mean is actually unknown. We can calculate the sample mean of the income from the sample of 57,000 households. If the sample is well chosen and representative, the sample mean should be very close to the unknown population mean of income. This is essentially how statistics work. This example is about Xenical capsules. Xenical is a drug used to treat obesity in people with risk factors such as diabetes, high blood pressure. A standard prescription of Xenical is given in 120 milligram capsules. The actual weight may vary slightly. In order to estimate the variation, we may take a sample of 10 capsules and calculate the sample standard deviation. In this example, the population contains all capsules, and the sample contains the 10 capsules selected. The population data are weights of all capsules, and the sample data contains the weights of the 10 selected capsules. The population measure is the population standard deviation of the weights of all capsules. Because we do not have the data for all capsules, we cannot calculate this population standard deviation. So the population standard deviation is unknown. What we can do is to calculate the sample standard deviation from the weights of 10 selected capsules. Therefore, we can use the sample standard deviation to approximate the unknown population standard deviation. This is another example of point estimation. We want to introduce another concept called standardized variable. For variable x, the standardized version of x or the standardized variable is calculated by subtracting the mean mu and then divided by the standard deviation sigma. After standardization, its mean is always 0 and its standard deviation becomes 1. In many applications, we may standardize data before analysis. For an observed value of a variable x, the corresponding value of the standardized variable z is called the z-score of the observation. The term standard score is often used instead of z-score. In this example, the length of holes on the Augusta National Golf Course have mean 413.1 yards and the standard deviation 132 yards. The standardized variable can be written as z equals x minus 413.1 divided by 132. The juniper's length is 180 yards. Its z-score can be calculated by replacing x in the formula by 180. The value is negative 1.77. Let's check another one. The camellia's length is 495 yards. Its z-score is 0.62. A z-score reflects the relative standing of one observation in a dataset. What does it mean? Recall the empirical rule. 68% of observations are within one standard deviation of mean. The two endpoints of this interval is mu minus sigma and mu plus sigma. If we calculate the standardized variable for these two variables, we get -1 and +1. Therefore, in terms of the standardized variable, 68% of observations are within -1 and 1. Similarly, we can say that 95% of observations are within -2 and 2 in terms of the standardized variable, and 99.7% of observations are within -3 and 3 in terms of the standardized variable. If we know that an observation with z-score 2.0, we will know that this observation is larger than 97.5% of the data. Why 97.5%? Look at this graph. Locate the value of z equals 2. If you add the percentage corresponding to the areas to the left of z equals 2, you will get 97.5%. In the previous slide, we calculated two z-scores, negative 1.77 and 0.62. If we can locate negative 1.77 and 0.62 in this graph to get their relative standing.